So is the screen visible to you? Like, is this PPT visible? Hello, now is it visible? I have just exited and started again. Okay, so now is the PPT visible? Okay, so for the students, so thank you, Amrita. So this the question is a 480 thick slab is hot rolled using a roll of diameter 720 So for a coefficient of friction of zero point 0.5, the maximum possible reduction in is given by. So that is this particular. So I thought that actually the slide was visible to you. So students, in case it's not visible to you, please do communicate immediately. Otherwise, I'll go on explaining and I'll not be able to know whether my screen is visible or not. So please let me know. Yeah, so I hope this question is now visible to you. A 480 thick slab is hot rolled using a roll of diameter 720 So the coefficient of friction is given as zero point 0.5. The maximum possible reduction in diameter is given by dash. So there is one simple equation that you need to know in order to answer this question. So in case you're not able to answer, I'll be happy to explain. So you can take 2 minutes to see if you can get the equation, so else I'll explain. So are you able to get the equation or should I explain? Yeah, so that is the correct answer. So basically we have mu as the coefficient of friction, r is the radius of the roll, and delta h max we have to find out. Delta h max is equal to 90 So is Kamesh also getting the same answer? Hello? Okay. So I'll move on to the next question. There was some issue with my laptop, it seems. I thought I was audible and visible, but it seems I tried multiple times. So I'll try to rectify that for the next time. So sorry, guys. So we'll move on to the next question. The critical value of Gibbs energy of nucleation at equilibrium temperature is dash. So first you need to find the Gibbs energy equation. How to find out the change in Gibbs energy. So is anybody able to come up with the equation? How to find the change in Gibbs energy? No, that is not actually required here. Here we need to find out only the critical value, right? So we need to find the critical value of delta G. So what is the equation for delta G? A very simple direct equation we usually use. Should I present? Yeah. So Gibbs free energy change can be expressed as delta G is equal to minus RT ln K. So you might have learned this in thermodynamics of materials, right? Yeah. So in this particular equation, at equilibrium temperature, what will be the value of K? So at equilibrium temperature, the value of K will be 0. Sorry? No, no. K is activity, but what will be the value of K? K will be 0. So, and we have to substitute the value of 0. And once we substitute the value of 0, what will be delta G finally? Ln 0 will be. Yeah, exactly. So the final answer will be delta G is equal to infinity. So it's a very direct question. It was asked for 1 mark in 2013. So is this clear to you? Okay. So we'll move on to the next question. So next question is about arc welding. Arc welding is done using current voltage and welding speed of the three different values are given to you: 200 amperes, 20 volt, and zero point 0.1 meter per second respectively. The heat input in kilojoule per unit length is given by dash. So it was asked for 1 mark in 2013. So are you familiar with the equation for arc welding? So this also is a direct substitution question. You just need to be familiar with what is the concept of arc welding and what is the equation for finding heat input in case of arc welding. Somebody has responded through chat, I feel. So 400 kilojoule. That is the correct answer. So Kamesh, if you can please unmute and explain what is the equation that is used, it would be useful. Yeah. Okay, since there, yeah, tell me please. Sure. Yeah. 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 And there is a point zero 0.06 in the numerator as well. Yeah, so this is the basic equation. Thank you, Kamesh. So this is the basic equation that we used in case of arc welding. So the welding heat input required formula is given as HI is equal to AV zero point zero 0.06 by S, where HI is the heat input required. Either we can express it in kilojoule per unit length, that is kilojoule per mm, or we can directly express it as ampere volt per mean per meter. So A is the arc welding current in ampere, B is the arc welding voltage, and S is the welding speed in mm per minute. So please note here that here voltage as well as current is directly given in whatever we want to substitute, that is 220 volt. But please note that S is given in meter per second and we actually require is mm per minute. So we need that conversion before substituting. So here the given values are 20 volt, 200 ampere, and S is given as 0.01 meter per second. So how to convert that meter? We have to convert into mm. So we multiply it by 10 power minus 3. Second, we have to convert it into minute. Therefore, we divide it by 60. So finally, we'll be getting 0.01 into 60 into 10 power minus 3. And once we have got all these values, we can directly substitute. That is 60 into 20 into 200 divided by what we have got for S, and finally we will be getting 400 kilojoule per mm. So here we have got kilojoule per mm, that is what exactly implies kilojoule per unit length. This per unit length means per mm. So the answer would be 400. So is this clear to you, Mr. Chanta? Yeah. So we can now move on to the next question. That is, a polymer matrix composite is reinforced with long continuous ceramic fibers aligned in one direction. The Young's moduli of matrix and fibers are EM and EF respectively. The volume fraction of fibers is F. Assuming isostress condition, Young's modulus of the composite EC in a direction perpendicular to the length of the fibers is given by dash. So we have four options and it was asked for 2 marks in 2012. So during your theory course, you might have actually memorized this equation. So in case you remember, you will be able to identify from the options. So you can just give a random guess and see if it's correct. Otherwise, we'll be explaining. So should I explain or are you actually trying? Like you are trying right now to answer? Yeah, sure. What about Kamesh? I think he has not yet responded. So Yeah, so I think I'll go on explaining. So, when a material is loaded in the longitudinal direction, so here we have the matrix and the fiber, so it is given in two alternate colors. And when this particular material is loaded in the same direction as the fibers, that is in the longitudinal direction, the matrix experience the same stress or the strain as that of the fibers. So it is an isostrain condition. Both will be experiencing the same strain. But when the material is loaded in a transverse direction, the fibers and the matrix will experience the same stress. So these are the two cases of isostress and isostrain. So as the name suggests, isostrains means that both the matrix as well as the fibers experience the same strain, and isostress means that they both of them experience the same stress. So here we can say epsilon is equal to epsilon of matrix is equal to epsilon of fibers. Here similarly, in case of isostress, stress is common for both the matrix as well as the fibers. So when isostrain condition exists, the stress value will be a sum. Similarly, when the isostress exists, the strain value will be a sum. So what happens in isostrain condition? Displacement continuously occurs across the layers. But in case of isostress, the stress continuity is there across the layers. So discontinuity, actual displacement continuity means the strain. So that is the case of isostrain and isostress. So we are actually asked to find out what the Young's modulus equation. So, how do we convert stress and strain into Young's modulus? We have a very common relation, right? For Young's modulus, stress and strain. So, you might be knowing that equation. Yeah. E is equal, yeah. E is equal to, yeah. So, basically, stress by strain is a constant, but that constant is known as the Young's modulus. So, using that conversion, we can find out what happens during isostress and isostrain. So what happens is that, so in case of isostrain, elastic modulus of a lamellar composite, we already said that isostrain condition means that the strain of the composite is equal to strain of the fiber is equal to strain of the matrix is equal to epsilon. Sorry, here we'll be taking the total applied load as a sum. On multiply on dividing the load condition with respect to area, we will be getting the stress. Therefore we can get sigma is equal to P by A, and P can be substituted as sigma into A. Therefore what happens, sigma C, that is the composite stress multiplied by composite area is equal to the stress and the area of the fiber and stress and the area of the matrix. And here we have to substitute what, the sigma has to be replaced by the Young's modulus equation. So dividing this particular equation by epsilon and the area of the composite. So when we divide AF by AC, we get the volume fraction, right? So that is the amount in a particular composite, the fraction of the fibers as well as the fraction of the matrix. So AF divided by AC gives us the fraction of fibers. AM divided by AC gives us the fraction of the matrix. So fraction of the matrix is given by VM and fraction of the fibers is given by VF. And on dividing sigma F divided by epsilon, we get the E values. We know that epsilon values are all same, right? Therefore, by dividing sigma by epsilon, we get the Young's modulus value. Hence, in case of an isostrain condition, the final equation will be EC is equal to EFVF plus EMVM. So, this is the case of an isostrain. So, in our particular question, they have asked for isostress condition. So in isostress, we already know sigma C is equal to sigma F is equal to sigma M. So we can take that as sigma. C stands for composite, F stands for fibers, and M stands for matrix. So the total change in length, let's say delta L C, is given by change in length of the fiber plus change in length of the matrix. Suppose we know the equation for strain, right? Delta L by L is the strain. So this delta L will be replaced by LF into epsilon F, where epsilon F stands for the strain in the fiber. Similarly, delta LM will be replaced by LM into epsilon M. This is from the normal strain equation. And finally, epsilon of the composite is given by delta LC divided by LC. And what happens on substituting, we get similarly, we get volume fraction of the fibers and volume fraction of the matrix. Therefore, epsilon C is equal to volume fraction of fiber into strain of the fibers plus volume fraction of matrix into strain of the matrix. So we have got that. Now we need to replace all these epsilon values by our Young's modulus equation. That is what we do here. Epsilon c is given by sigma by ec, epsilon f is given by sigma by ef, and epsilon m is given by sigma by em. Here we are taking sigma because we know that in isostress condition all three have the same value. So upon substituting and solving, what do we get? We find, so we can take from here itself. Let's see. So 1 by ec is equal to vf by ef plus vm by em. So in our particular equation, vf is given as f, that is the volume fraction of fibers. So summing up both the fraction of fibers and metrics will give us 1, right? Therefore if vf is equal to f, then vm will be equal to 1 minus f, because summation of both of them will be equal to 1, because it's a volume fraction. So when we are replacing this particular equation, what happens? We get 1 by ec is equal to f by ef plus 1 minus f divided by em. So this is the particular answer that we require for our question. So is this clear? Yeah, so basically what you have to know is, in isostrain condition, strain will be the same, load will be a summation. In isostress condition, stress will be the same, strain will be a summation. And using these two concepts, you can substitute your basic equations, that is Young's modulus equal to stress by strain. On substituting and solving, you'll finally get 1 by Ez is equal to F by EF plus 1 minus F by EM. So that's the case of isostress and isostrain. Hence, for this particular question, then what will be the answer from A, B, C, and D? Just now we had mentioned. Yeah. So that is the correct answer. So I hope it's clear to you. So is it clear to you? Yeah. Okay. So now we'll move on to the final question. So for a BCC metal, the ratio of surface energy per unit area of the 100 plane to that of the 110 plane is given by dash. So this question was actually discussed in a previous class. This is actually a recap question. So since exams are approaching, we are actually doing recap questions every week. So this is a recap question. So for a BCC metal, the ratio of surface energy per unit area of the 100 plane to that of the 110 plane is given by dash. So we need to know the equation for surface energy per unit area. So you can take a minute or two in order to see if you can come up with the equation for surface energy per unit area, else I'll explain. So are you able to come up with the answers, or should I explain? Should I explain? Hello. Hello? Yeah, am I audible right now? Yeah, okay. I'll present the last question. So there was a loss of connectivity in between, I guess. Yeah, is this visible? Hello? Is it visible? Okay. Okay, fine, fine, fine. So basically, the question is for a BCC metal, the ratio of surface energy per unit area of the 100 plane to that of the 110 plane is dash. This is a recap question. I've already discussed this, and in case you have seen my previous videos, it will be there. In case not, you can try attempting right now. So the first thing is you have to find the equation for surface energy per unit area. So should I explain or are you able to come up with the equation? Yeah, okay, sure. What about Kamesh? Are you familiar with this question? Okay, yeah, he might have gone through the previous video. Fine, fine. So I'll explain for you right now. So basically, the surface energy per unit area is given by an equation gamma ABC is equal to delta Hs by zero point 0.5 Na Cn of bulk divided by number of surface atoms into Cn lost by surface area. So, no need to be frightened by the big equations. Like most of these terms will be now converted into a constant and will be ignored. And only a few terms we have to finally consider. So, delta Hs is the molar enthalpy of sublimation, Cn is the coordination number, and Na is the Avogadro number. So what we do is that we are considering delta H is by zero point 0.5 Na. We are leaving and we are considering it as a constant epsilon. So fine, then we have the equation sigma ABC is equal to epsilon into number of surface atoms by surface area into coordination number lost divided by coordination number of the bulk. So this is basically the equation that you finally want. So there is some kind of constant, and since we are asked to compare the surface energy per unit area of two planes, we this epsilon will get cancelled. So whatever that remains is only these four terms: number of surface atoms, surface area, coordination number lost, coordination number of the bulk. So is still that part clear to you? This part, yeah. So we have a BCC unit cell. We know that coordination number of the bulk is 8. Now we have two planes, the 110 plane and the 100 plane. So if you are familiar with Miller indices, you might be knowing that this is the 110 plane and this is the 100 plane. Now we have to find out coordination number of the surface and coordination number loss. So what do you mean by coordination number of surface? So in this particular plane, when we are taking any one atom, this atom will be in contact with the atom at the center, this particular atom, and one atom above. Same way, it will be in contact to three other atoms on the adjacent unit cell. Hence, coordination number of the surface would be 6. So, coordination number of the bulk was 8, coordination number of the surface is 6, and therefore, coordination number lost is 8 minus 6 is equal to 2. So that part is clear. Now we need to find out the number of the surface atoms. So in this particular plane, how many atoms can we identify? There is one fourth here, one fourth here, one fourth here, one fourth here, which contributes to one atom, and there is one atom at the center. Therefore, and plus, therefore, total number will be number of surface atoms is equal to 2. Similarly, for this particular plane, coordination number of the surface, this atom will be in contact with this atom, this atom. Similarly, one above, one to the side. Therefore, coordination number of the surface will be 4. And therefore, coordination number lost will be 8 minus 4 is equal to 4. Number of surface atoms, how will you calculate? 1 by 4th is here, 1 by 4th is here, 1 by 4th is here, 1 by 4th is here. Therefore, total number of surface atom will be equal to 1. So, we have all the required values in case of 110 plane and the 100 plane. So, is still that part clear? Okay, coordination number of surface, you see this particular atom at the corner. You have to think how many atoms it is touching. So it is touching this atom at the center. It is touching this atom. Similarly, it will be touching an atom above also, right? Yeah. Ye- Yeah, exactly. So one is here, and one is at the center. Similarly, here it will be contacting a particular atom, here it will be contacting, and it will be contacting something at the center of the adjacent unit cell also. Therefore, we have total number of coordination at the surface as 6. We have to think how many atoms it is actually touching. So if you can't visualize this particular plane, pick up this particular plane. So here what happens, it is touching this. Even though we draw a unit cell like this, all the time it is assumed that these walls, right, all these are touching each other. So this particular atom will be touching this one and this one. Similarly, it will be touching one above and one to the side. So we have to think how many atoms that our atom under consideration is touching. That is how we get coordination number of the surface. So here it touches. Yeah. So now we have got all the values. Now we have to start substituting. Epsilon we know is a constant. Surface atoms we have calculated. 110 means it is 2. Number of surface atoms in 100 it is 1. So that we have got. Now coordination number lost is the difference between 8 and this value. So 8 minus 4 we have 4. Here we have 8 minus 6 we have 2. And coordination number of the bulk for both cases is 8. And now we need to find the surface area. So this particular plane is a cube itself, right? So therefore we have A0 square. Here what happens, this is kind of a rectangle. So this is a diagonal and this particular length is root to A0. If this is root to A0 and this is A0, the total area will be given by root to A0 square, isn't it? If this is root 2 a0, since it is a diagonal, this will be equal to a0 square plus a0 square, and therefore this length will be root 2 a0. If this is root 2 a0 and this is a0, total area of this particular plane can be a0 into root 2 a0. Therefore, it will become root 2 a0 square, right? In that case, when we are substituting, we have gamma 110. So this person has to go up, this has to come in the denominator. Epsilon of both cases, it is a constant, we are neglecting them. So coordination number lost here is 4, coordination number of bulk is 8. Coordination number lost here is 2, coordination number of bulk is 8. Here, number of surface atoms is 1 and the surface area is A0. Here the number of surface atoms is 2 and the surface area is root 2 A0 square. So upon solving and cancelling, we will get it is equal to root 2. That is why the answer comes as 1.414. So is that clear to you? Yeah. So that is how we find out the ratio of surface energy. So finally our answer will be 1.414. Since our 1 hour has almost been approaching, so this is all for today's week. I hope you are clear with all of the questions that we have discussed so far. In case you have any additional queries and feedback, please do email me at sandra.pmrf@gmail.com. So thank you for spending time with me. So prepare well for gate examination that is approaching. Thank you so much. Now you may leave the meeting. Thank you so much. Yeah.